All right, so kinematics. So first thing we went over in kinematics is, or was, scalars and vectors. We reviewed that from Science 10. Okay, we went over what quantities were scalar, what quantities were vector, what it meant to be scalar versus vector. Okay, so scalar quantities have magnitude only. Okay, well, vector quantities have both magnitude and direction. Okay. And then our scalar quantities throughout the course have been things like distance, speed, time, energy, work, frequency, period, okay, things like that. Okay, our vector quantities throughout the course have been displacement, velocity, acceleration, force, amplitude, yeah. Okay. So it's not really a matter of like, I'm going to test, oh, which of the following is a scalar quantity? I mean, I probably would have done that in Science 10, but I'm not likely to do that on a Physics 20 final exam that only has 21 multiple choice questions. I'm not going to waste a question on that. But do you need to know whether something is vector or scalar for a lot of calculations? Yes. Yeah. Okay, that part of it is huge. Okay, remembering that if you're calculating, net force, that you might have to draw things tail to head, okay, and do vector addition on them, okay, things like that. So just keep that kind of stuff in mind. That's where you need to know what things are vector and scalar for how you treat them mathematically. We also reviewed that day V equals d over t and V equals d over t. Okay, again, not going to have a single dedicated question on V equals d over t anywhere on your final exam, but it is part of a lot of things. It could be part of an echo question. It could be part of a projectile motion question. It could be part of a graphing question. Okay, it's involved in a lot of things we did in this course. Okay, so obviously you have to be able to use V equals d over t, and at this point that's something you can't do. Well, that's a problem. Okay. All right, after that, we moved on to graphing. And there is definitely graphing on the final. Okay, specifically, we looked at two different types of graphs. The same two that we looked at in Science 10, position versus time and velocity versus time. Okay, we also did a lot of this. A lot of y equals mx plus d. Okay, so there's a couple multiple choice questions that involve graphing. They're more interpretation, like tell me what's going on in the graph kind of things. Okay, not so much calculation. But there's some written response that's going to involve using graphs. Okay, could be y equals mx plus b. People's children. Okay, could be y equals mx plus b, could be just regular stuff. Okay, so let's look at a couple of graph, position versus time graph situations. So let's say I've got a position versus time graph that looks like that, and I'm told that y equals 5.6x plus 13.2. What's the velocity of the object in that graph?
5.6
Right, 5.6, what?
meters per second.
Yeah, meters per second. I put meters and seconds on that graph, so it would definitely be meters per second. And I would say positive, right? For that, because velocity is a vector quantity, and that is clearly increasing the change in position. Okay. Could I also ask you to calculate how long it would take to reach a certain position? Yeah. Okay. Could I ask you from that graph to calculate what position it would be at after a certain amount of time? Okay. Those would be the things I would ask. They're what I asked you to do on your graphing lab, okay, that we did. So I would ask you the same things on a test if I gave you a y equals mx plus b position versus time graph. Okay. The other way I could give you a position versus time graph is I could make it look kind of like this. Okay, so this would be meters and seconds. Okay, could I ask you to calculate the total displacement?
Yes.
How would you do that?
The area of each.
That would be for a velocity versus time graph.
VF subtract V,
There's no V's on this graph.
or PF subtract V.
Right, PF minus PF. Okay, final position minus initial position. Okay, that would get me the total displacement. Could I then also ask you things like the total distance traveled? How would I do that?
Calculate each line
Yeah,
segment.
exactly. I got to calculate how far it goes in each line segment. So here it didn't go anywhere because it's flat. This would be a certain distance. Doesn't matter whether it's positive or negative because distance is scalar. Nowhere, a little bit of distance. Nowhere, a little bit of distance. Okay. Yeah, you'd have to do those calculations. Certainly something I could ask. I could ask you to calculate the average speed over the whole trip or the speed during any particular part of it as well. Okay. Things I couldn't ask you. Well, I could, but it'd be a one-mark question. What's the acceleration during part A? 0. What's the acceleration during the last part?
Positive.
Nope.
0.
Also 0. Okay? In the first part, the object's not moving, so it's also not accelerating. But in the last part, it's traveling at a constant velocity in a forward direction, which also means it's not accelerating. What does acceleration look like on this kind of graph? Curve, right? Okay, little things like that, right? Interpretation. It's been a while since we did anything like that, so it's good to have a bit of a refresher. Okay. Next thing. Okay, what's the initial velocity of that object?
19.2.
19.2 meters per second, right? Because the y-intercept would be how fast it was going at time 0. What's the acceleration of that object?
2.7
2.7
meters per second.
meters per second squared, positive, forward, yeah, something like that. Okay, little things to remember there, right? Remember that for both of these graphs, the slope is calculated the same way, right? M equals y minus b over x. Same here. But on this graph, y is my final position, b is my initial position, and x is time. That calculates velocity. On this graph, y is vf, b is vi, and x is time. That calculates acceleration. Okay. That's not something we want to memorize. We can figure that out on any graph. Okay, what does the slope represent on this graph? Well, what's on the y-axis? What's on the x-axis? Okay, this is what it represents. Okay, it's better to analyze every graph than try and memorize every graph. So I could ask you those two questions. I could also ask you, what's the total displacement?
That would be the area.
That would be the area. Okay, so for this one here then, that would be a rectangle and a triangle. Right? Now I already know, I would know what x was, so I know the base of the rectangle, and I know what b is, so I know the height of the rectangle. So that would be just base times height. Okay? I would have to calculate what y is at this x to get the height of my triangle. It would be y minus b to get the height of my triangle, and multiply that by the base, divide it by 2. Okay? Really, when I do those area calculations, what I'm actually doing is taking average velocity and multiplying by time, which calculates d. Okay? Because on the bottom here, that rectangle is implying constant velocity of whatever b is. Okay? And then for this one, the velocity is changing, so I take the height of the triangle and divide it by 2. Well, halfway up the triangle is the opposite, is the average velocity. Okay? Multiply that by the time, and I've got my displacement. Okay? Because it's changing uniformly from this value to this value. So right smack in the middle is where my average is. That's why we can go base times height over 2. It's the height that's over 2, right? Okay. All right, is that making sense? Okay. What's the object doing in the last part?
Going forward.
Okay, it is going forwards.
Is it accelerating?
It is accelerating forwards. Okay. It's accelerating forwards. Is it moving forwards for the entire last part? It's not. Right down here, it's still moving backwards because velocity is still negative. It's at this point right here where it changes direction. Okay? We had a question about that on both the unit exam and the day we went over velocity versus time graphs, and I spoiled it. I said, this will be on the test. And then it wasn't. Because, well, that's what they do. Okay. All right, you ringing a bell for the graphs?
Yep.
Okay, so definitely expect something, like 1 or 2 out of those 4 things is going to be on there. All right, then we talked about acceleration. Actually, we didn't. We started into vector addition, but I'm going to say we did acceleration before we do vectors. Okay, so there could be multiple choice question. There would be like a simple kind of acceleration thing, maybe even a simple calculation. But I'm more concerned with the problem-solving aspect of acceleration, okay? And that would be using any of the formulas we went over in class. Okay, don't write those down, they're on your formula sheet. Okay, I see a bunch of you scribbling, don't. Okay, those are all on your formula sheet. Should you be proficient in the use of all of those?
Yes.
Yes. Okay, there may or may not be just a simple acceleration problem, but acceleration was part of projectile motion, it's part of velocity versus time graphs, it's part of Newton's second law, okay, Newton's third law, it's part of all of that. Okay, so we definitely need to be able to use our acceleration formulas proficiently because it's going to be on there. Okay? All right. Then, vector addition. Okay, how do we add vectors? Tail to head, right, we draw them tail to head. So if I had Okay, so it would look something like that if I was doing vector addition. Okay, so I would have that first vector being 10 meters at 40 degrees north of east. Okay, my second vector would be 8 meters at 20 degrees south of east, right? And then the blue line is my resultant. Okay, so how do I find my resultants now that I've drawn the diagram, which we found was really the trickiest part of all this?
You need to find the X and Y for that result.
Yeah, I've got to find the X and Y for my resultant, and in order to do that, I've got to find the X and Y components of each one of the vectors I was given. Okay, so if I wanted to find black X, okay, trigonometry, I'd use the adjacent side, it is the adjacent side, so cos of 40, okay, times 10 meters, okay. Black Y would be the sine of 40, because it's the opposite side, times 10 meters. Okay, and then for my red one, okay, X would be the cos of 20. Is X always cos? No, it just happened to be that way because of the way I drew it. It could be either one. Okay, times 8 meters, right? And Y would be the sine of 20 times 8 meters. Okay, and then I would take those X's and Y's and put them together to get my resultant. Now, what do I need to keep in mind when I'm putting the X's and Y's together?
Where they would match up. So like for like the blue line, you have to take the black line subtracted by the red line.
Right. I have to keep in mind which way those Y and X components are pointing. Both the X components are east, so I can add them together. That's no problem. But black Y is pointing north, and red Y is pointing south. Okay? Which means I have to take into account that it's backtracking in the Y dimension. Okay? Everybody with me there? Then I would have blue X and blue Y. Then I could do Pythagorean theorem and get the displacement's magnitude. And then I would have to do trig, okay, in order to get the angle. So tan to the -1 of Y over X. Okay? We did so many of those, but I guarantee you there'll be a vector addition question on your final exam. Okay? And was vector analysis also part of Newton's second law? Right? Force, net force is the vector sum of all forces. So in the interest of keeping a test short, would it be something I might do to make the vector addition question a Newton's second law question? Because then I can test two things in one question. Yeah, I'm not mean. Okay, it is possible. Okay? You certainly need to know how to do it. Okay, and then after that, we went on to projectile motion. So here's the thing about projectile motion. It has v equals d over t in it. It has vector components in it. It has acceleration in it. Is that a great way for me to test half of Unit 1?
Yes.
First question in the written response. Spoiler alert, that's true. Okay. Yeah. Were there two kinds? Okay. And so we had the projected at an angle, which involved vectors, and the kind that went projected horizontally, which was basically just v equals d over t in acceleration. And we did tons of those as well. That's what's in there from Unit 1. Seems like not very much, but we spent quite a bit of time on vector addition in that unit because we needed it again in Unit 2. All right. Anything you would like for me to review in more detail or questions you'd like to ask about this one?
Can we go for a projectile motion question?
Gee, I'm so surprised that question came up. Okay, I'll give you a few minutes on that one. See what you remember. All right, so this is a projected at an angle problem, okay? It tells us that the projected velocity is 21 meters per second, 30 degrees above the horizontal. That means that the rock is going to travel through a projectile arc that will re-encounter the ground over here. Okay. As with any projectile motion problem, there are two dimensions to this problem. Okay, and so that means we want to break it up into the vertical part and the horizontal part. Okay. Now, as it stands, that 21 meters per second contains a horizontal component and a vertical component. The vertical component of this is going to be the initial vertical velocity, because that's all they tell us. It was thrown like this. That's at like time 0. Okay? It's initial because vertically the object is going to accelerate due to gravity. Okay. Can I calculate what VI is, given the information I have?
Yes.
Yeah, because I have the hypotenuse of this triangle and an angle within it. Right? So VI is the vertical component of that triangle, and it is going to be the sine of 30 times 21, which will be positive 10.5 meters per second. Now, according to what we know about projectile motion, it was thrown from the ground and it re-encounters the ground over here, okay? Which means the displacement over the entire trip vertically is 0. What does that mean for the final velocity? It's the same as the initial, but opposite in direction. Okay, so that's what I have from a vertical perspective. From a horizontal perspective, we know that horizontally, since they didn't tell us that this wasn't in a perfect system, we assume it was, that the velocity horizontally is going to be constant. That means it's not going to change as it travels through the air. Okay, there's no air resistance or anything like that. Okay, so it's going to be constant, which means I can calculate it right now. It also means that horizontally, I want to use that formula because the speed is not changing. Okay. So V horizontal is the adjacent side, so that'll be the cos of 30 times 21. Okay, so that side's going to be 18.187 meters per second. Okay, at this point, that's all I can get from the diagram. Now I've got to calculate stuff with the numbers I calculated. Okay, what can I calculate with the vertical information that might be useful to me? I could calculate maximum height right now. Yep. I was thinking of something else. Time. I want to use V equals d over t, right? They wanted to know how far this thing travels horizontally. If I'm going to do that, that means I'm looking for d. I only have v right now. I need t if I'm going to get d. All right? And it's also handy because there's more than one way to calculate the maximum height. One of those ways uses the time. Right? So I might as well calculate the time right now. I have all the information here that I need to do that. Okay, so I'm going to have A equals VF minus VI over T. Okay, and I'm going to manipulate that for T. So T will equal negative 10.5 minus 10.5 divided by negative 9.81. All right, so I'm getting 2.14 seconds as my time. Okay, so now I can bring that 2.14 seconds over to the horizontal part, because both the horizontal and vertical parts only happen for that long. After that, the rock hits the ground. Okay, so now I know over here. So now I can do this. D equals V times T. So I take my 18.187 and multiply it by 2.14 seconds, and I'll have the horizontal distance traveled. Okay, so the rock is going to travel, we only have 2 significant digits here, so 39 meters. Okay, get asked how far does it travel? Do I need a vector on that? No. Okay. The other thing the question wanted me to calculate was the maximum height. So here's what I have to remember about the maximum height. It occurs here. How fast is the object going vertically at that point? Right. Its velocity vertical at that point is now 0 meters per second. Or, the second method I could use, at what point in terms of time does that happen? Halfway. Okay, so I could solve this one of 2 ways. Okay, the way I prefer to do it is this way. I go VF squared equals VI squared plus 2AD, and I solve for D. Okay, so D will equal VF squared minus VI squared over 2A, and so that will be 0 minus 10.5 squared divided by negative 19.62. Okay, that's 2 times 9.81. So 0 minus 10.5 squared is that, divided by negative 19.62. Okay, so the maximum height is going to be 5.6 meters. Okay, the other way to do this is using this formula. Okay, perfectly legit to do it this way, as long as I remember to do what with the time? Yeah, divide it in half. Okay, so I'm going to have 10.5 times 1.07, okay, but I'll put all the actual decimals in there, plus 1/2 times negative 9.81, okay, times 1.07 squared. Okay, so go back up. Oh, I have 10.5 as actual. Okay, so 10.5 times that number plus 0.5 times negative 9.81 times that number squared. Gee, look at that. That's exactly the same number. Okay, everybody all right with that one? There's actually a third way. I could use D equals VF times T minus 1/2 AT squared, and I would also get that answer. Okay, so any of those ways work. All right, what else?
Can we go over some graphing?
Graphing, okay. graphing was already built here. Using this graph, okay, give you a few minutes to see if you can do 1 and 2. Okay, so obviously for question number 1, the calculation's the same for all 3 carts. You just plug in the different slopes, okay, instead, and the different y-intercepts. Okay, so for each one in question number 1, it will be that we are looking for y, okay, for each one. So for cart number 1, actually we'll do cart number 2 because it's red. Okay, so cart number 2, we're going to go 2.01 times 55 plus 0.00952. Okay, and then for
It says negative 0.05 for the,
oh, for the answer? Okay.
no, for the, y-intercept for plus b.
0.0 is 10 to the negative 3.
That's the blue one.
That's the blue one. What is going on here?
Uh-oh.
All I got. Okay, so for cart 1, since I can't even seem to erase it now, we got, sorry, this is 0.0524 and it's negative. Okay, for cart number 1, 1.38 times 55 okay, plus 0.00952. Okay, and for the third cart, 3.39 times 55 plus 0.0381. Okay, everybody with me on that one? Okay. And then for question number 2, how long will it take for each cart to travel? Okay, so we manipulate for x. X is y minus b over m. Okay, so for each car, so if it was car number 1, we would have 65 minus 0.00952 divided by 1.38, and the others would follow suit with their appropriate numbers. Okay, just plugging in. Everybody okay with that one? Now, velocity versus time graphs. For this one here, that I would like for you to calculate, oh shoot, I picked a bad graph. All the y-intercepts are negative. Okay, imagine the y-intercept for each of those is for the green one is 0. We'll just imagine, pretend that it's 0. Calculate the total displacement of that object to 1.5 seconds. Okay, for the green line. Okay, the displacement of the green line to 1.5 seconds, assuming the y-intercept is 0. Okay, so we'll just cross this out. Oh, there we go. So there's like 2 steps to this. Okay, so for this one, okay, we're going to assume that the y-intercept is 0. We need to go and find the area underneath the line, because that'll be average velocity times time, okay, for the green line to 1.5 seconds. Well, we don't know what the y value is at 1.5 seconds because it's off the graph. Okay, so we have to calculate that. Okay, so y will equal 1.45 times 1.5 plus 0, because we said the y-intercept is going to be 0 now. Okay, so first we have to do that calculation to get y. All right, so we're going to get 2.175 meters per second. Right, and now we can do the triangle calculation. So we're just going to go base times height over 2. So 1.5 times 2.175 over 2. So that's time multiplied by average velocity. Okay, and that's going to equal displacement. All right, so the total displacement to that point is going to be 1.6 meters. Okay. All right, so I won't ask you to do anything much different than that in terms of graphics. Okay, what else?
A vector addition problem?
Vector addition problem, okay. I may have even had one on here. Nope. Okay, so. Okay, 10.2 meters due east, or due west, sorry, and 16 meters at 20 degrees south of east. All right, so we're going to have, okay, our diagram, we got 10.2 meters due west. And then we've got 16 meters at 20 degrees south of east. Okay, so this is due east, so I'm just going to go back east. Okay, that was weird. Okay, and I'm going to go 20 degrees south of east, so that's going to be like here. What the heck? Blue. There's our 20 degrees, 16.2 meters. I think I've done a decent job of drawing that to scale. The blue line is about 1.5 times longer than the black line, okay? And so that means it ends up back over here. This will be its X component, this will be its Y component. It should just completely overlap. Like if I was doing this really properly, okay? Like that would be right there. Okay, and then my resultant is going to go here. Okay. And it'll have an X and a Y, and that'll be theta, and this will be my overall displacement. So that's what your vector diagram should look like. Oh,
Sorry, is it 16 or 16.2?
16, oh sorry, just 16, sorry. All right, give you a little more time to get working on the math of that one. Okay, so if we're looking at this one here, we'll start with the first one. Okay, the X component of our 10.2 is 10.2 meters west. Okay, the Y component of that is 0 meters because it doesn't go north or south. Okay, for our blue triangle, okay, the X component is going to be the cos of 20 times 16. okay, is 15.03, or 04. Meters, and that is east, okay? And our y component is going to be the sine of 20 times 16. Right, which is 5.47 meters. Okay, now that we've got those, now we can start working on adding the x's and the y's together, right? So if I want to get my resultant's x component, okay, I've got 10.2 meters west and then 15.04 meters east. Okay, so I'm just going to go 15.04 minus 10.2. I could add a negative if I wanted to, but in the end this is going to work out pretty much the same. Okay, so using all of my decimals, okay, is 4.835 meters east. Okay, because we went further east than we went west. Everyone okay with that so far? Okay, my y component is easy because I only went south, and I only did that during the blue part of the trip, so it's just 5.47 meters south. It doesn't require any extra calculation. All right, now that I've got that, I've got the two sides of my triangle. This one's 4.835, and this one is 5.47. All right, so now I can find d using Pythagorean theorem. Okay, so it'll be the square root of 5.47 squared plus 4.835 squared. Oh, sorry, I need to use the whole number. Squared plus squared, square rooted. All right, so we got 7.30 meters. Okay, as the magnitude, and then I got to find theta. Okay, so for me, I'm going to use 10 to the minus 1 of the opposite side, which the way I drew it is y. So 5.47 divided by 4.835. Again, I want to use all of my numbers here, so second tan of that one divided by all right, so that gives me 48.5 degrees. And that'll be south of east. Okay, and now I've only got two significant digits, so my final answer would be 7.3 meters at 49 degrees south of east, or possibly at 41 degrees east of south. Either one of those would be acceptable. Okay, that ringing a bell? Okay. What do we got? All right, anything else we want to go over in the last 5 minutes?
Could we go for another projectile motion question?
Not in 5 minutes, but I can put one up there. Okay, car drives off a cliff, 6.2 meters per second. It's a very slow car. Okay, 6.2 meters per second, and hits the ground 25 meters from the base of the cliff. I want to know how high the cliff is. Okay. All right, so we have a vertical and a horizontal part. Okay, the vertical part is undergoing accelerated motion. 9.81 meters per second squared. The big thing here is we have to remember, since it was projected horizontally, that our initial vertical velocity is 0. Okay, we're looking for the vertical distance traveled, okay, which is D. We don't have time, but we can get it from here, okay? Time is gonna equal D over V, so 25 divided by 6.2, okay? We'll take that time and we'll put it here, and then we can use D equals VI times T plus 1/2 AT squared. This will be 0, so basically it's just 1/2 times 9.81 times whatever that time comes out to, and that'll be the height of the cliff. Okay? All right. So, tomorrow, unit exam. Okay, if you normally write in learning support, go straight there. Your test's already waiting for you. Okay, and if not, come here and you can get started right away. Same as always. Okay, and then on Wednesday, we'll go over that test and do some dynamics review. Okay, and then Thursday, we'll work on some other stuff, whatever you guys want to work on.